Hey there, welcome back to our channel. In today's video, we'll be exploring an essential concept in electrical circuits, the transfer functions. Transfer functions provide valuable insights into how signals are transformed within a circuit. So let's jump right in. Before we dive into transfer functions, let's quickly recap what they are. In simple terms, a transfer function describes how an input signal gets transformed into an output signal within an electrical circuit. It represents the relationship between the input and output signals. Mathematically, a transfer function is typically represented using the Laplace transform. The Laplace transform is a mathematical tool that allows us to analyze and understand the behavior of linear time variant systems, such as electrical circuits. The transfer function, denoted by h of omega, is the ratio of the output signal y of omega to the input signal x of omega. Here omega represents the frequency. The transfer function provides crucial information about how the circuit processes the input signal to produce the output signal. It helps us to analyze the circuit's behavior in terms of amplification, attenuation, phase shifts, and frequency response. To better understand transfer functions, let's consider a simple circuit, an RL circuit. In this RL circuit, we have a resistor, an inductor, and a voltage source connected in series. The voltage source is frequency dependent. We can see now when the frequency is very low, there will be a very small amount of voltage drop across the inductor because the inductor opposes a change in current. If the change in current is slow, then the opposition to the change will be very small. But as the frequency rises, the opposition to the change in current will increase. So we can see as the frequency rises, the transfer function increases because the transfer function is the ratio to the output voltage to the input voltage. The ratio is frequency dependent as the output voltage and the input voltage is dependent on the frequency. The transfer function yields a number between 0 and 1. A 0 represents a bad transfer or no transfer, and a 1 represents a good transfer. So here in this RC circuit, we know a capacitor acts as a short circuit for very high frequency and a open circuit for very low frequencies. So in low frequencies, the capacitor acts as an open circuit. So here and here we have the same voltage as the source voltage, but as the frequency rises, the capacitor acts more and more like a short circuit, and when the frequency reaches to infinity, the capacitor becomes almost a short circuit. So then there will be no voltage drop across the capacitor. So that's how the frequency affects the transfer function. Now let's take a look at the types of transfer functions. There are basically 4 types of transfer functions. The first is the voltage gain, the second is the current gain, the third is the transfer impedance, and the fourth is the transfer admittance. The voltage gain is obviously the voltage ratio of the output voltage to the input voltage. The current gain is also self-explanatory, is the current ratio of the output current to the input current. The transfer admittance is the ratio of the output voltage to the input current, and the transfer admittance is the ratio to the output current to the input voltage. The transfer impedance of a network is the ratio of the output voltage in one mesh of a network to the input current in another mesh. So it describes how the voltage of one mesh affects the current through another mesh. The transfer admittance of a network is the ratio of the output current at one node in the network to the input voltage at another node. So that wraps up today's video on transfer function in electrical circuits. I hope you find it informative and helpful. If you have any questions or suggestions for future videos, please let us know in the comments below. Don't forget to like and subscribe to our channel for more exciting content like this. Thanks for watching and see you in the next video.